Okay, good morning, students. So it's just to like so where we now yeah, hello. So we are in the week 8. So Friday, so we are going to complete the lecture 16. So that is this is the first week of the fourth chapter. Okay, so which is the nuclear physics. So then we have big time. Nuclear physics, the next 3 weeks of the lecture for the chapter 4, nuclear physics. Then the last 2 weeks, so week 11 and 12, then we will go into the atomic and the quantum physics. So the lesson, okay, so it's progressing according. So the lesson is progressing according to what is according to what is planned in the scheme of work. Okay, just to highlight to you all, in case some of you all, if you feel it is too slow and so on, that is the pace because I'm looking at an average of all the students. So not to be too fast and not to be too slow also. And that's why we have the scheme of work to guide us, okay, to ensure that we are, okay, so around that, okay, but we cannot be on dot perfect. Okay, so yes, okay, so suppose, okay, so I should have exactly start the chapter 4 on this week, but then in initial last class, okay, so we did discuss a bit questions because I took up the time to discuss the question. Otherwise, I would have started with the chapter 4. Okay, so just to clarify on that, and then assignment updates. Okay, so the submission, soft copy submission deadline is coming Tuesday, 11:59 p.m. Okay, so once it goes into the third, okay, so June, then soft copy submission will not be accepted. Okay, so but the hard copy, okay, so you can submit today in here, this box here. Okay, not the box that you find, that is for the practical report. Okay, so or you can also submit Wednesday, so during the lecture. Okay, so same like this. Okay, so that's the only two time where you can submit your hard copy of your assignment. So some things to clarify because this is based on some questions that's been asked. See, when you look at the cover pages, okay, so there is two. One is the course submission form. The course submission form is the same as what when you use for the practical. So that is the individual student's declaration form. So therefore, when you submit your assignment, so in a group, if you have 4 members, all 4 members has to fill up the course submission form. It is the declaration of your involvement in the assignment. Okay. And then, okay, that is the 4 pages. For example, a member 4 members. So then on top of it, then you will have the cover page of your assignment. So the cover page will have a column for all the members. You write all the details of the members in the group. Okay, so that will be a cover page, followed by the submission form. Then followed by your report. Okay. So your assignment, submissions, format, or we can say order. So sometimes when I say, okay, so then some may be not able to That's it. So order. So first you will have your cover page. Second, you have the submission form. This one is individual. Individual. This is the group details. So all the members, okay, so with your student ID. Third is your assignment report. Report. Okay, some good. I can know that some of you all have arranged, okay, so to conduct an experiment. Some have done a video recording of the experiment that you have done. Okay, so yes, show proof. Okay, so you have done, you have taken an effort. So if just say you have done the experiment, okay, so then if you want to attach, I mean you have recorded what you have, the activity that you have taken place. So if you want to share to me at the last page of your report, you can attach the link of the video. So on the last page. So you can say the link, okay, so to the experiment, okay, so conducted. Okay, so then I can just click. So you can upload into your, I mean, you can upload to YouTube and so on. Okay, and share the link. Okay, and then uh, you will upload that. I mean, you will submit that in your Moodle. So I can just click and watch. So don't submit the video. Okay, so don't upload the video. It will take up a lot of space. So attach the link. It's easier for me to click and watch. Okay. So I hope that is clear. Oh, sorry. So I hope that is clear. Okay. So 1, 2, 3. Okay. So then that comes as the last page. Okay. We can just leave that page. So you can write the title as the link to the video. Okay. So for the experiment, then you can attach the link. Then you can just close it by end of the assignment. Finish. Okay. So at the end, you can. Okay. I hope this is clear. Anything further? Is there anything to clarify? So far, that's what I think a common thing is asked. Another thing is, okay, so past and present tense, okay, so passive form. Okay, so it is follows the same standard, okay, of the practical, the full report that you have done. Okay, so you write in past passive form. Okay, so I think I will, in the themes, I have also answered that. Okay. So then other than that, I didn't get any question. I thought I actually attached that in the assignment instructions, but then I just checked through. Okay, so I didn't include that. But okay, so as been advised for the full report, so we will follow the same thing. Okay, so because this is not a compulsory, okay, for you to do the experiment. Okay, so because looking at the limitations and so on. Okay, so even yesterday night also I received an email. Okay, so asking for me to sign to use the lab. Okay, I did this morning already. Which group? Okay, so I already written the sign form to you, so you can arrange. Okay, so today and see. Okay, so that's on the things to clarify. So coming back to your scheme of work, okay, so We are. Okay, so according to what need to be, according to the schedule. So we had the practical on a spectrophotometer. Next week will be a tutorial week. Okay, so your tutorial, then followed by the next two practicals, which is on a spectroscopy and also radiation detection of natural sources. And before the last, and then the last week, okay, so we have a tutorial four, okay, so to cover up, okay, so okay for the semester, okay, and then coming back to the next week Friday. So I did mention that, okay, so earlier. So next week Friday I will on leave, and after some discussion with the class, I mean with the class rep group, so I could not. It's very difficult to find a slot 1.5 hours for us to slot in the class to replace. Okay, so therefore, okay, so I have suggested that we will extend. Okay, so the classes on the normal Wednesday and Friday to cover up that. Okay, so just say if you are able to extend half an hour, then 3 sections we will do that. So if you are not able to, okay, extend, okay, so then we have more sections. Okay, so but generally, okay, so 3 sections. So we don't want to drag too much. So this week, today's lesson, the first lesson, okay, so we will have any of the group having a lesson at 11 o'clock, 11 a.m. Huh? 11, okay. So maybe 10 minutes before, okay, on Wednesday, 11, any group have a lecture at Wednesday, 11 a.m.? No, you all have. Okay. So then we will not stretch until the 11th. Okay, so probably about 11, because I couldn't, we could not agree with any time. Okay, so therefore, that's the only, because I need to submit a leave application because this is bragging. Okay, so I could not, unless I have to take a emergency leave. Okay, and for the group for the Monday, okay, settled because next week Monday is a public holiday, but the group tutorial session is settled. Okay, so I'm having you all okay agreed to Monday evening, fine. Okay, so Friday there is a tutorial session for the which group? Huh? So many groups. Okay, so Friday tutorial. So the physical science 6 and physical science. So physical science 6 and physical science, the tutorial is supposed to be 11 to 12 and 3 to 4. Okay, 3 to 4, we can maintain that. Okay, so online. Okay, so for the group physical science, but for the group physical science 6, okay, so I will discuss further. 11 to 12 is cannot because that is the time I'm involved in the family event. Okay, so that's the purpose will be away. Okay, so therefore it has to be pushed later in the afternoon. So I will check with the class rep. So but that 2 sections will be online because I will be out of town. So I won't be here. So I have to conduct the sessions online. Okay, so later I will communicate with the class rep. Okay, so I just wanted to ensure that. So for the most important is the lecture. So the lecture, okay, so unless we can have a day to replace, then we can go ahead on a day to replace. Okay, so if it is not next week, maybe we can also decide to replace it on the following week. Yes, can. So because I think next week there's some group having quiz on Tuesday. So if it is the following week, Tuesday, if possible to have the replacement, week 10, then we will go ahead with that. Okay, so I don't want to, see, I also don't want to extend the class because 1.5 hours, I can see your mode is already, the absorption level, okay, already reached. So I cannot push some more, okay? So I don't want to do that also. So we need to have something effective lesson so you are able to follow. Okay, so class rep, okay, take note. Okay, so can you please come back to me? Okay, so how? Okay, so do you, is that okay? Okay, so week 10, we can fix a replacement class week 10. Okay, so probably Tuesday. Okay, so which is after the, I mean, evening, lah. So 5 to 6:30 or something. Okay, come. I think that's all. Don't want to take much time. So it's already 9:20. Sometimes these instructions is what takes up some time. But otherwise, I can see the information is not getting across. Okay, not many have also checking the themes. Okay, so please check your Moodle, some updates. Okay, so in the Moodle, I already have posted the question paper and the answer marking scheme for the quiz in your Moodle. Okay, so under the quiz, okay, so you can check it is been shared there. Okay, so fine. Let's move on. Okay, so here, last class, we have been talking about the nucleus symbols. Okay, so how we can actually represent the information about the nucleus. So we have the mass number. Okay, so mass number, which is also known as nuclear number. See, mass number is the old term. Okay, so older term, okay, we use mass number, but now we use the nucleon number. Okay, so total number of protons and the neutrons in the nucleus. So that will be on top, A symbol. Then below you have the atomic number, which represents the number of protons, okay, so in the nucleus. And basically, when you look at the nuclear number, this is referring to the number of nucleons in the nucleus. It does not take count of the electrons. Okay, that's why we call it as a nucleon number, which is the number of particles that is basically found inside the nucleus. So then from there, you abstract out the proton. So that gives you the atomic number. So whatever that you see, okay, so in this information about a nucleus, it only provides information on the nucleus. So it does not give you any information about the outside, the number of electrons. Okay, so, but we will know whether the nucleus is a neutral nucleus or not by referring to the charge. So if you just say if you have a negative charge, okay, so a positive charge, that will indicate the majority, okay, is that an electron or it is a proton. I think that you learn that in your chemistry. Okay, then, okay, so I think nucleus X, so that's X nucleus X having a mass number of A and atomic number, that's detailed. So, and then if you want to find the neutron number, so you'll take A, U minus Z. So when the nucleon number minus the atomic number, so you'll get your neutron number. Okay, a very simple thing. Make sure that if it comes out in the exam, don't lose mark for this. Okay, so a nuclide is a nucleus or atom having a specific atomic number and a specific mass number. So example, you can see carbon. Here you have carbon 12, carbon 13. Sorry, carbon 13 is not there. So you have carbon 14 and carbon 12. So in fact, there is also another carbon, carbon 13. These are isotopes of carbon. So hydrogen, you have 112131. Okay, that is also referring to the isotopes of hydrogen. Okay, so this is how you present your information about a particular nucleus. I mean nuclide, sorry. So a particular nuclide in referring to the details of the nucleus. So isotope, I did mention this now. So isotopes of an element are nuclei having the same number of proton but different number of neutrons. You can see. So just now I mentioned for carbon, you have another one which is 13C6. So you can see that all the proton numbers, okay, so the proton numbers, sorry, So all the proton numbers are the same. So what will be different is the obviously the neutron. So when you take 14 minus 6, 13 minus 6, 12 minus 6, so that will actually give you the neutron number. So the neutron number is going to be different. Because the neutron number is different, that's why your nucleon number, okay, so the mass number is also differs, but the proton number is the same. So when we refer to isotope, so isotope is referring to the same element, but they have different neutron number. Okay. And then when you look at the hydrogen here, so hydrogen you have 1, 1, 2, 1, and you also have 3, 1. Mono, dwi, and tritium. Monotherium, deuterium, and tritium. So these are the three isotopes for the hydrogen, which has also the same number of proton, but they have different number of neutron. So then you can just read up this point. I think these are basic that you have learned. Okay, so the first point mentioned, isotopes of an element have a same atomic number but different mass number. Okay, so isotopes of an element have a same chemical properties but different physical properties. Okay, so why? Okay, so what is the idea? Okay, so which is explains why their chemical property does not change. Okay, so but the physical property changes. So if you look at the proton number, they have the same number of proton. So when they have the same number of protons, okay, so in terms of the charge, okay, so it is the same. So therefore, the chemical property will not change. But the neutron number is different. So the composition of the nucleons, the number of nucleons, it is changes. So it can be lighter or it can be a heavier, denser. Okay. So that will influence the physical property. So physical property in terms of the temperature of melting point, boiling point. Okay. So what do we say? Uh, the ability to vaporize. Okay. So there's a term in chemistry. Okay. So flowability, yeah. So the ability to flow of so flowability, all that will vary because that is a physical property of a material. Okay. But the chemical property will not change because they have the same proton number. So if that particular nucleus has a charge of 2 positive, meaning it's going to have 2 positive, even though it's a different isotope. So the reaction rate will be the same. So the chemical property will not change. Okay, so that is about how the character of the isotopes. So here it is the examples I mentioned just now. Further to can refer. So then for the carbon. So for carbon, you can see carbon 12 is the normal carbon, which is kindly basically found in a, I mean, it is found in a live living thing. But when that, I mean, for example, if it is if it's dead, then it will go through a decay process. So then it will produce a carbon radioactive. So the carbon radioactive, you can have a carbon radioactive, which is carbon 13 and carbon 14. So this is how in archaeology, okay, so archaeology, you know what is archaeology? Archaeology, what is that? What is the field of archaeology? Yeah, it is a field where you mean they will find, okay, so it's a carbon dating. Okay, so based on the activity of a carbon, they will determine the age of a fossil or age of something that they have found. So this is how they predict the age of some fossil bones that has been found. How do we know what is the age of the a time where the dinosaurs was around and so on? It is based on analyzing the carbon dating. Okay, so the activity of the carbon, okay, detected from the bone. Okay, so Any questions? So oxygen also we have isotope, oxygen 16, 17, and 18. Okay. So then you can just this O. Okay. This is a space here. Could you please fill up the space? So for carbon 12, 12 minus 6, you get 6. Okay, so this is to fill up the number of neutrons. So you have 6. 13 minus 6, you have 7. Okay, so 8. So basically that is the number of neutrons. Okay, I no need to call anyone to come and answer that in front. Huh? Okay, so 16 minus 8, okay, so 8. 17 minus 8 is 9. 18 minus 8 is, okay, 10. So that is how you can calculate. Okay, so maybe in the exam not that easy lah. Okay. So if any questions so far? If we send, we move on to discuss about the nuclear force and stability. So this is explains to us why when you talk about a particular nucleus, okay, so when you are referring to a sample of a sample of a radioactive, a nuclide, why there is some nucleus which is stable and some nucleus which is not stable. Okay. So it is due to the composition of the nucleus, which is the mixture of protons and also the neutrons. So this will actually decide the stability of the nucleus. So if you look at the points mentioned, so nuclear force and stability, okay, just bring through first. So we have a strong nuclear force is the force that keeps the nucleus together. So we have a strong nuclear force. This strong nuclear force is due to the mass. It can be due to the masses of the nucleus, which is the proton and also the neutron. Even though the proton and neutron has smaller mass, but still, okay, so they have a mass. The mass is small, yes, proton and neutron. So the mass of the proton is about 1.67 times 10 power minus 27 kg. Mass of a neutron is also almost the same, 1.67 times 10 power minus 27. So, but even though the mass is a small number, but they have a mass. So when there is a mass, there will be a force, okay, a nuclear force, which will attract. Okay, it's like a nuclear gravitational force. So it will attract. On top of that, okay, so in the nucleus, we have protons, okay, so which is positively charged. Okay, so neutron, no need to worry because it is neutral. But the protons are positively charged. So what happens? Same charge. They will repel each other. So this will produce a repulsive force between the nucleus. The repulsive force between the protons. So there is an attractive force and there is also a repulsive force. So when these forces are balanced, then you can have a stable nuclei. But if these forces are not stable, for example, the repulsive force is much stronger than the attractive force, then you will expect the nucleus will not be stable. If the attractive force is greater than the repulsive force, then they can attract. So the nucleus is stable. So this is what causes a situation whereby a nucleus can be stable and unstable. So you look at the point. So strong nuclear force is the force that keeps the nucleus together. Okay. So it is an attractive force between and two nucleons. Okay. So two nucleons. So this attractive force, okay, between the two nucleons, it can be either between proton to proton, or it can be between proton to neutron, or it can be also between neutron to neutron. That is the attractive force, because this is dependent on the mass. Anything which has a mass will experience the attractive force. Then it does not act on uh, electrons, because electrons are outside. Okay, they are outside of the nucleus. So electrons have nothing to do with the stability of the nucleus. Okay, so the electrons are outside the shell. Okay, so outside the nucleus. So the shell. Okay, so on a different energy levels. Okay, so it is a short range force acting only over nuclear distance. So we see no evidence for the nuclear forces outside the nucleus. Okay, so when they say it's a short range force, so these forces, they don't, you don't see the significant far distance. It's only a short range only, because like we are talking about something that is very small, very micro thing. So it is within the atom. So it is a short range. Okay, so we are talking, distance, we are talking about a distance which is a very small distance in a micrometer and so on. Okay, so we see no evidence for the nuclear forces outside the nucleus. Yes, so there is no evidence outside. Okay, it does not act on the electrons. Okay, so it is not acting on the electrons, because the electrons are, it is quite far. See, when you compare between the size of an atom and with the size of the diameter, there is a large difference. So when you compare between the size of an atom and the size of a nucleus, a simple, this is the atom and this is the nucleus. Okay, the size of the atom, which is the diameter. Okay, so up there. So the diameter of an atom, this one, it is about times 10 power of minus 10 meter, where the size, the diameter of the nucleus, this one, diameter of the nucleus, it is in the order of times 10 power of minus 15 meter. Okay, so it is minus 10 and minus 15. So obviously we can see the size of the nucleus. Okay, so the size of the diameter of the atom, it is 10 power of 5 times greater, bigger than the nucleus. So therefore, look at the space inside. So you have a huge space. So the electron can be anywhere inside here. So the distance is far. So that is already a long range. So it does not have much influence, okay, so on the nuclear force. So that's what they meant by here. Over a range where it acts, it is stronger than the electrostatic force that tries to push two protons apart. So in a short range, okay, so we find that the force due to the nuclear attractive force, it is stronger than the repulsive force due to the electrostatic. You have done the chapter electric, okay, so electrostatic. So you have definitely seen, okay, so when they are same charge, so they experience a repulsive force. Okay, so this is about the forces, okay, so within the nucleus. So what I have explained is basically this is what, okay, so it is putting into a more diagrammatic way to explain. Okay, so when you are referring to the neutron, neutron, proton, proton, okay, so neutron, 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 proton, okay, so they experience the attractive force. Proton, proton, okay, same charge, they will repel each other. Fine. Okay, look at this graph. So this is a graph which shows how the nuclear force and the stability of a nucleus. So this graph is plotted. Neutron number, which is on your y-axis, okay, neutron number on your y-axis versus the proton number on your x-axis. Okay, neutron number on your y-axis versus the proton number on your x-axis. Okay, bigger. Okay, so you will notice that first thing is look at the line n equals to z. So when they say n equals to z, that means that is the ratio y equals to x. So meaning the number of neutrons equivalent to the number of protons. Okay, that is actually just a reference. So the line is drawn there is just for the purpose of a reference. Okay, then you look at the line here. So this line which is drawn, okay, it is the line of stability. So it is a line, okay, a best fit line that is drawn, not a straight line. It is slightly is a curve, which covers the stability region for the nucleus. Okay, stability region for the nucleus. Okay, so but we do find around that stability, the line that you draw, okay, line of stability. So you can see there is like a kind of a shaded. Okay, so for example, you see like this, it covers. So meaning these are all the possible nucleus which is stable, and this is the area where cover. So what do you see within that space, the area, okay, so which is kind of like a shaded, that is the region of stability for the nucleus. So any nucleus which is falls within that space, the area region, then they are stable. They don't really go through a radioactive decay process. Okay, so they are stable, so they don't go through a radioactive decay process. Okay, so they're stable very well. Okay, so therefore, why they need to decay? The idea of a radioactive decay is the nucleus is not stable. It has to decay. Okay, so in order to become a stable nucleus. So if it is already stable, then what is the purpose of going through a decay process? No need. Okay. So any questions? So you can see further, you can see some points has been explained. So for example, if you look at this, unstable nuclei are two bands, okay, so along the both sides of the line of the stability. Okay, you'll see the unstable. Okay, so the stable nuclei cluster, okay, very close to the line of stability. Okay, and do you able to analyze, able to see this in your diagram or not? Okay, I will take out the boundary. Okay, don't want the boundary. Okay, all clear. See, if you look at to analyze this graph, I want you to analyze first, okay? Because I will just keep on talking. So I want you to analyze. Tell me, listen, tell me how the shift of the stability takes place when the number of protons and neutrons are increasing. How the shift of stability is taking place when the number of neutrons or protons are increasing. The shift that is taking place is actually, I'm talking about the ratio between the number of proton and neutron. So that is what the shift I'm looking at, the shift. So what is the change in the ratio of number of protons and neutrons, okay, for stability when the number of protons and neutrons are increasing? I hope you got the question. 1 minute. What you can say about the change in the ratio of the number of proton and neutron? Okay, so for the stability, when the number of proton and neutrons are increasing. But you can tell about the ratio, the change in the ratio of the number of proton and the neutron. Okay, so for the stability and the number of proton and neutrons are increasing. When you look at the graph, you should be able to analyze it from the graph.
You see that number of protons is increasing.
So how the ratio of the number of protons to the neutron changes is for the stability.
It's one to them increasing the same one.
Okay, yes. So but how the ratio changes? The ratio of the number of proton and neutron. That's fine. Yes, we can see the number of protons and increases, the number of neutron increases. Okay, so but we get the right. But how the ratio changes? Okay. Ratio becomes I don't know. Okay, how we were able to analyze this? Okay, if you look at not the line which is y equals to x. Look at the line of stability. The line of stability you observe is actually slightly curving upward, right? Okay, it is curving upward. So that means as the number of protons increasing, okay, you need to have more number of neutrons to balance up the process. That's why you can see the curve is going up. So it's getting steeper, in fact. Okay. This is something, yeah, in detail we analyze. So you can see this is the curve. So it's going up. So it is from here, it is getting steeper and steeper. So for increase in the number of protons, okay, so sorry, those who are behind pillar, okay, sorry. So for increase in the number of protons, okay, so the number of neutrons need to increase more to balance up the forces between them. So because when the number of protons are increasing, what will happen? There is going to be greater repulsive force, correct or not? When number of protons increases, more positive charge. More positive charge, okay, so they will repel more. So in order to balance up the repulsive force, you need to have more neutrons to come in to balance the attraction. Okay, that's why you can see the ratio of number of neutrons to the protons is actually increases. Okay, so when the proton number is increasing. Okay, it's just like when two fellow fight, you will probably one person is enough to stop the fight. If three fellows are fighting, then you need more people to help to settle the thing. Okay, you have 10 people fighting, then probably you have equal you need equal number of people to settle it. Okay, it goes like that. Okay, so yeah, so this is just to for you to understand. Otherwise, you just memorize. Okay, so the graph. So you'll not know, okay, you don't analyze in detail of why the shift is taking place there. Okay, so yeah, so when more protons goes in, okay, so it is going to cause a greater repulsive force, okay, to between the protons. Okay, yes, there is an attractive force, proton. Okay, so but in order to balance it up, I need to have a attractive force coming in. So neutrons are being added. We cannot add proton. Okay, proton, then it will increase the repulsion again. So we need something to bring them together. Okay, attraction. Okay. So what is being discussed is actually what is further you can see in the points here. Okay, so just go through fast. Graphically, the stable nuclei cluster is very close to the line of stability. So there are no stable nuclei which is greater than 83 bismuth. Okay, you can see when a nucleus goes beyond the proton number, okay, so which is equivalent to 83, you will notice the stability is not more, sorry, not any more stable. The reason is it's too heavy already. So the nucleus is too heavy. It already have too many protons and neutrons. So it will not be stable. So it has to go through decay process. That's what we will discuss in when it comes to the binding energy part. Okay. So which is, if the nucleus is too heavy, so some example is if a person is obesity, okay, so too much, put on too much of weight, obesity. So what has to be do? It has to go through to reduce the weight. So to come to if you want to be a fit person, so you have to reduce the weight. So the same thing happens in the nucleus. So if a particular nucleus is heavy, then it has to go through a process of what we call fission. Okay, a fission reaction. We will actually discuss that later. But anyway, since I mentioned, so a larger nuclei, okay, if we want to change to smaller, okay, then it has to go through a series of fission reaction. Okay, but if it is from smaller, smaller, if we were to change to larger, okay, if it is like too small, okay, change to larger, then it will go through a fusion reaction. So these are the two process of decay. Okay, fusion and fission reactions can be experienced by a nucleus for the nucleus to become stable. Okay, so we will be touching on that. So they are okay. So mentioned. So unstable nucleus are in the bands along both sides of the line of stability. So the lightest element, which is less than 16, are stable when almost, okay, you can see the number of protons is equivalent to number of neutrons. So you can see when usually the nucleus which is less than 20, so the ratio of number of proton and the number of neutron are 1 to 1. They are equal, 1 to 1. They are stable. Okay, so for lighter nucleus, they are stable with a ratio of 1 to 1 for proton and neutron. But as they get heavier, then we need to have more neutrons to stabilize the nucleus. Okay, I hope I have been clear. I mean, I have explained that clearly to you. So, as the okay, the nuclear number increases, the number of neutrons needed to stability grows increasingly larger than the number of proton. This was the statement which I was asking just now. Okay. So it's now 9:56. We take a break. Okay. Oh, attendance. Lecture 16. This one is signed, or this one is for the proposed practical. Oh, lecture 16. Lecture 16. Oh, because I accidentally thought Tuesday is the sorry. Sorry. Six, five, attendance. Okay. Yes. Oh, what's enough?
For the submission form, if we have 3 members, then we need to.
Three submission form. The cover page is just one.
So the stability is considered, it's not stable because the total number is the neutron.
The balance of the proton and neutron.
Yeah, so basically the neutron number is more than the proton number, which leads to it being unstable.
Yeah, when the number of neutrons are less than 20, you can see the ratio 1 to 1 is fine. For neutron 1 to proton 1. But as the nucleus become heavier, you see it is already shifted away from the ratio 1 to 1. So you need to have more neutrons to balance. So if they say if you have 10, below anything that is 10 proton number, so if you have 10 proton, 10 neutron will be enough to balance. But it's for 10, which is smaller proton number. But when the proton number increases, for example, if your proton number becomes 60, then 60 neutrons is not enough already. I need to have like 70 neutrons to balance. So the number of neutrons ratio will be higher. So we need more to balance.
Then how
That's
about
why the graph is shifting upward.
then how about the protons and the repulsive force? So if the protons get like too high to a certain extent, then it will also affect the stability, right?
Yeah, that's why when the proton is too much, you need to have more neutrons to balance it. Because the neutrons can cause a attractive force. So they can hold to balance the repulsive force. Okay, that's why you need more neutrons to come in. Okay, yes.
Before you this we are very dark and
Oh.
okay, because I think
Mhm.
it says that the voltage consumption of is possible. But I think the scope details and the declaration and the signature is already in one. So can we still use this form or we need to print?
Because because it is going to be a group work, so it is also counted as an individual involvement. So that is a process. Okay, so where we need to also have the individual declaration inside. So when you sign, so you must.
I declared here already. Yeah.
On behalf of everyone for
Yeah.
Since you already done, then it's fine. Okay.
So we can just submit this.
Yeah. Okay.
Okay. So one more thing.
Yeah.
I don't know how to name the file when I submit the soft copy of the. Do you have a specific format to name the file to submit?
Oh, okay. You can the group leader. Okay, so you can submit. Okay, so the group leader. Then which group, which class? Not your group, because you have the same group in a different class also. Right? So your group one, group two. So your group in your class lah. So you're from physical science.
One.
So physical science one. You put physical science one. Okay, so the person who's submitting and your ID.
Name my ID and then the class.
Yes. So then I can refer back lah. Because I have this hard copy. So I mean, I already have the list of the group members, so I can check from that. Anyway, give it a put a note here. Okay, so
There's our door. So can we submit now if we have done everything?
yeah, can be.
Double check. So can we have a double check first?
Yeah, wait. Then you take it, drop it in the box.
Either we can probably believe that in individual declaration, but I found the source of the for the group one, who can we just pass out like this?
Once you have already done, then fine.
Okay.
Okay.
So I just pass out the detail right now.
You just can drop it in the box like that in the box. Yeah. The one you drop it in the box.
Yes, here, right?
Yeah. Yeah. Huh? Oh, okay, sign. Sorry. Okay. Ali, I didn't see you just now. Now you are in the class. Hey, hey, hey. Okay. Some I saw earlier went out. Okay, so I have not written back. Okay, so if you already plan to cheat me, then whichever way you can actually cheat me. Okay, so coming in late. Okay, so come in, then you go out, then you don't return back. Okay, so okay, so see how you progress in your exam. Okay, your future, your life, your future, you decide, your responsibility. We can just guide you. There is a saying, okay, you can only bring the horse to drink. You cannot force the horse to drink. Okay, so stop. Atomic mass. So these all are some chemistry terms, means some things that you learn in your chemistry. Okay, so 1 mole of a carbon C12. Okay, so it is said to be equivalent to 12.000 gram. A mass of one single carbon. Okay, so 12 atom. This is when you are referring to one carbon atom. Okay, so when you say 1 mole of a carbon atom, so that 1 mole means, there's my point. That 1 mole mean it is equivalent to Avogadro constant, Na. It is 1 point. Avogadro constant. What is the Avogadro constant value? 6.02 times 10 power of 23 atoms. So, if 1 mole equals to 12 gram, okay, so which has 6.02 times 10 power of 23 atoms, therefore, what will be the mass of one atom? So, therefore, you take 12 gram, you divide it by the number of Avogadro constant. Okay, so, and when you are changing it to kg, then 12 gram, okay, so times 10 power minus 3, it becomes kg. Divide by the Avogadro constant value. So, that gives you 1.99 times 10 power minus 23 kg. That is mass of one carbon, one atom of carbon, a single atom. Okay, so and from there further, so you will find this constant which is known as the atomic mass unit, AMU. Okay, so atomic mass unit. So one atomic mass unit, it is equivalent to 1/12 of the mass of one carbon 12 atom. So meaning it is just now you got the mass of one carbon atom, single carbon atom. So when that is divided by 12, okay, because one AMU, atomic mass unit, is equivalent to 1/12 of the mass of one atom of carbon. So therefore, 1/12 you multiply by the value earlier, that gives you 1.66 times 10 power minus 27. So that is the equivalent value of 1U. Okay, so I'm not sure how much you use this in your chemistry, but when it comes to the chapter nuclear physics, especially when you discuss about the binding energy and so on, we will be using these details. Okay, so in doing further calculations. So take note. So one atomic mass unit, 1U, it is equivalent to 1.66 times 10 power minus 27 kg. So further from that, okay, so you have these constant values. You're not going to prove the values. It's just recall, okay. You know, okay, definitely that in the data booklet, these values are also given, provided in the formula list. So you can refer to the values. Okay, so I'm not going to further explain. But obviously you can see the mass of the proton and the mass of the neutron, okay, over here. So the mass of the proton and the mass of the neutron, they kind of almost the same, minus 27, which is almost close to the 1U value. Okay, but 1U, okay, so it is 1.66. Okay, but here is 1.67. That is the mass of proton and neutron. But the power wise is still the same, minus 27, minus 27. Electron, okay, you notice the electron is the light. Okay, so it's much lighter than the proton and neutron. Is almost about 1,842 times lighter than the proton or neutron. Okay, you can just take 167. You take any of the value, you take proton or neutron, then you divide by 1,842 and see what you get. You can take any of this value. Okay, so you divide by 1,842. What do you get? You can round it up to 1,840 also. Didn't matter. Anyone, please work it out and give me the answer. Is that close to 9.11 times 10 power minus 31? I mean, do you get minus 31? Yeah, is that right? Okay, yeah. So that proves that the electrons are Okay, so 1,800 times lighter. Okay, so than the protons and neutrons. That's why neutron, I mean, that's why electron. So that's why electrons are fundamental particle. Okay, protons and neutrons are not the fundamental particle. Okay, so I did mention about that before. So atomic mass. So atomic mass, we know it is equivalent to the, so when you talk about the atomic mass, which is the mass of the atom. This whole thing, if I want to find the atomic mass, so it is the mass of the atom, the whole thing. So it will be equivalent to the nuclear mass plus the total mass of the electrons inside the atom. So if you say I have I have electrons there. So I have 1, 2, 3, 4, 5, 6. So I have 6 electrons. So it has to be 6 times the mass of the electron plus the mass of the nucleus. So that will give you the total mass of the atom. Understand? Okay. So sometimes you need to see the difference. See, you have a mass, okay, atomic mass, and also the nuclear mass. So when you are referring to a nuclear mass, then it is only referring to the nucleus. So if just say like earlier, we already know the atomic mass. So we take the atomic mass, you minus the mass of the nucleus, sorry, mass of the electrons, then you'll get the mass of the nucleus. So nuclear mass. So you should be able to understand, okay, what is the atomic mass is referring to and what is the nuclear mass is referring to. Okay, atomic mass is the overall mass of the atom. But when you say nuclear mass, mean is only nucleus, excluding the electrons. Okay. So if you have atomic mass, you can minus off the mass of the nucleus. I mean the mass of the electron. Okay. So this is one example. Just okay, try. I know it's not much challenging. But anyway, this was the practice. So, what is the nuclear mass? Okay, you need to be clear of what the question is asking. Huh? So, what is the nuclear? Oops. Change to okay. What is the nuclear mass of a helium-3 if its atomic mass is 3.016030 U? So how do you work out? So if you want to find the atomic mass, mean you are looking at the whole mass of it. But what's that? The nuclear mass. Okay, so it is given. So if I draw a diagram, okay, so this is nucleus. So the atomic, when you're referring to the atomic mass, okay, so you know the total atomic mass is given by this value. So what is the nuclear mass? So you must take the atomic mass minus the nuclear mass. Okay, so if you want to find the nuclear mass, so it's equivalent to the atomic mass minus the minus what? Minus the minus what? Electrons. Okay, so the number of electrons. So atomic mass is, I have 3.016030 U. So U we know is 1.66. Okay, so we can use the, okay, so usually when you use, when in the even a data booklet, the value is given is 1.66 lah. So I can take 1.66 times 10 power of minus 27, unless if the question itself they have given you the AMU value, okay, so more precise significant, then you use the more precise data. Okay, so minus, okay, how do I calculate the electron? There's no information about electron here. Okay, found the mass of electron in data booklet. Okay, mass of electron. Okay, so that one is, we know 9.11 times 10 power minus 31. But how many electrons? Okay, so here if you look at it, this is a helium, 3,2 helium. And this is a neutral because there is no charge. So meaning they are neutral. If there is 2 protons, which is 2 positive, in order to compensate the 2 positive, you must have 2 electrons. So 2 negative. So therefore, the number of electrons here is 2. So it is 2 times the charge of a, sorry, not charge, the mass of the electron, 9.11 times 10 power of minus 31. Okay. So therefore, give me the answer. So that will give you the answer in kg lah. So kg, okay, when you work out, what do you get? Is that 5 point something? 5.00? Do you get 5.004788 something times 10 power of minus 27 kg? Okay, this is in kg. But if just say I want to change this answer into the in AMU, so I will divide this with the charge of mass of the the unified atomic mass value, which is 1.66 times 10 power of minus 27. So minus 27 can cancel. So I can take 5.00478878 divided by 1.66. So that will give me an answer somewhere about 3.014 U. So this one we are giving the answer in the form of unified atomic mass value. Okay, unified atomic mass value. So very common. Okay, so we will try to give the answer in a form in a unit of kg or unified atomic mass. Okay. Okay, so I will just move. Okay, now you look at the second example. Given that the nuclear mass, okay, I know the time is 10:31, so I need to take extra 10 minutes. Okay, so to cover up what? Okay, so I'm spending this to taking the time, okay, so to do the questions. Okay, so example 2, example 3, example 4, example 5, example 6. Okay, oh, sorry. This one all example only, where okay. So we do example 2 for today. Before we go back to okay, so then after that it starts with the mass defect and the binding energy. So you will have a strong understanding about the stability of the nucleus. You can refer to the graph we discussed just now, why there is a stable nucleus, why there is an unstable nucleus. So where the process of fission and fusion comes in. So before we go into further in finding the mass defect and binding energy. Okay, so back to, okay, given that the nuclear mass of a helium, okay, given 4.001506 U, find the mass defect of a helium nucleus. Okay, so we have not gone into the mass defect yet. Okay, but see, when you say a mass defect, okay, so it is referring to what is the mass as loss, or there is a change in the mass that have taken place. Okay, so during any process. Okay, for example, now I know what is the total mass of the nuclear mass of the helium. It is given in the question. Okay, so the total nuclear mass is given. And then they also give us the mass of the proton and the mass of the neutron separately. So don't worry about the electron here, because when you talk about the mass defect of a nucleus, okay, so it is the mass defect of a nucleus. We are referring to nucleus. So don't worry about the electron. Electrons will not come in. Okay, say, I know in this there is 2 protons. How many neutrons are there? How many neutrons are there in this nucleus? 2. So now 2 multiply the value. Can you give me? Okay, so just say is, okay, what is the value for 2 MP? So find for 2 Mn. Give me the value. It has to be accurate. Huh? So I mean you must multiply 1.007276. So what do you get? So when you multiply by proton, do you get 2 times this? Okay, I don't have the value calculated. Can you give me? So 2 times. So obviously you have 2.0, huh? 1, 4, 5, 5 again. 5, 2. That's it. U. Okay. What about 2 Mn? 2.01733 U. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Eh? How come goes one less number? 1, 2, 3, 4, 5, 6. Eh? Why now one number missing? 3, 3 what? Oh, 0. Okay. Okay, U lah. Okay. So now can you find the mass of 2 MP plus 2 Mn? So add them together. 2.01455. What do you get? You should get 4 point something. 4 point 4.0318882 U. Right? Okay. Now you compare this value. Okay, you compare this value with this value. Are they same? But they're supposed to be because this is both are basically information about the nucleus. But the nuclear mass that was 4.001506 U, that is the nuclear mass of the helium. Okay. But when you find the mass of the proton and the mass of the neutron separately, you got 4.031882 U. There is a difference. When you take them separately, the mass is greater. When they combine, the mass becomes lesser. The difference in the mass is actually what we understand as the mass defect. So what happened? Where this mass actually goes? So this is the mass that has been lost, which is been converted to a form of an energy. Okay, this is the mass that lost, which is been converted to a form of an energy. So when this comes together, so there is a okay, better. Okay, when it comes together, okay, so there is a loss in the mass takes place. That loss in the mass has been converted to a form of energy. Okay, so this is what you need to work in order to find the binding energy. Okay, so mass defect. Okay, so you just find the difference. So you can put it as delta M. Your delta M is equivalent to 4.03188 U minus 4.001506 U. So what do you get? The difference? So 0.030 0307. 037. Oh. So 037. Oh. Okay. So meaning, that's why I was wondering. There was another 0 here. Okay, so 0, 3, 7, 6. Okay. Yeah, so this is the mass defect. So once you know the mass defect, okay, where's the mass defect? Okay, for example, a simple idea, okay, where they have it can mean here, okay, so when they are separate, okay, so they have the masses, okay. When they come together, during the process of this fusion, there is some loss in the mass. So the loss in the mass is what is been converted to a form of an energy. And this energy that is being released, it is also is a measure of the stability of the nucleus. So if there is more energy is being emitted, so then the nucleus is more stable. Less energy is emitted, then it is less stable. So you have the energy that is emitted is what we understand as binding energy. Is the binding energy. It is one of the awesome, fantastic theory, okay, so which is being stated by Sir Albert Einstein. So whenever we think about Albert Einstein, okay, so the formula that comes into our mind is E equals to mc squared. Okay, so the mass is, you can refer to the, when you relate to this, is the mass defect. So when you found the mass defect here, which is 0.03037 U, okay, so 0.0303776. Okay, so 76 U. The U is actually equivalent to 1.66 times 10 power of minus 27. Then you multiply this with the speed of light, c squared. Where c squared is is the speed of a light is 3 times 10 power of 8 meter per second. Why we relate to the speed of a light? Because whatever the energy that is emitted, it is a energy in a form of photon energy, electromagnetic ray. So therefore, okay, it is emitted with the speed of light. Okay, so that is the theory that has been proved by Einstein. So with this, we can find the energy, and this energy is what the binding energy is about. So in the coming lessons, we are going to talk about in more bigger scope of the nucleus in related to the mass defect during a decay process that takes place. And from the mass defect, how do we able to find the binding energy and so on? And definitely this part will contribute a lot to your final exam. Take note. Thank you.
Shut down in progress.
Okay, bye-bye.